Okay, I told a lie in the last episode. It's been 5 minutes, not 2. Anyway, welcome back to Tectonics. It's been 5 minutes since the end of the last one. Hopefully it hasn't for you. Either it's been like 1 minute because you're watching through a playlist, or it's like the next one and it auto went onto it. Or it's been like 7 months and you haven't watched the other one. Go watch the other one. Or this is your first time in my very small, currently, community. Very close-knit, very fun, very something or other. I don't know any of you people, so but you know me. So we're united in knowing me. Hello. Yeah, this is your first time. Go watch the other one. Do it. Do it, or I'll hunt you down. And high five. Okay. Waste enough time. Here we go. So these are 3 plate boundaries, as I said last episode: destructive, constructive, and conservative. These 2 things can occur from these boundaries, which are volcanoes, and you know them, you love them, or you hate them if you actually live in a place with earthquakes, or if they're like small earthquakes, you get used to them, so you're non-committal to them. Earthquakes, volcanoes, and earthquakes. Now, there are 2 different types of volcanoes, and hundreds of thousands of different variations on an earthquake. Mostly the differences are just power. So, where can these occur? A destructive plate boundaries, you can have volcanoes, and you can also have earthquakes. I'll speed this up a bit. You can have earthquakes, and you can have earthquakes. Every single plate boundary, earthquakes. At constructive, you also have volcanoes, but not at conservative. That's simple. Done. Lesson done. Boom. What's it been? Like 3 minutes? Yes, so volcanoes are these 2, earthquakes are all 3 of them. Now, let's get rid of this. Let's go on to which one should we pick? Eeny, meeny, miny, mo. Eeny, meeny, miny, mo. Meeny, moony, moony, meeny, moony, moony, cow, coony, moony, moony, bajoony, that one. Let's do destructive. Okay, destructive. 3 types of destructive. Well, 2 really. What you can have is, well, no, hang on. Let's go do something else. Doesn't smell plates, does it? Plates. Got there eventually. There are two kinds of plates. The first kind is oceanic. Easy enough. It's a plate. It's under the ocean. This is very dense. This one, it's very dense. The other type is continental. Continental. That is a plate, and it's got like trees and stuff on it, and like buildings. I did say I should have been an artist, didn't I? And, well, you're very tall. In comparison to the tree in the house, you're very tall. This is like a short house. Shorty. So you're here, unless you're scuba diving. So unless you're here, you're there. The ground you're standing on is part of the continental plate, and that is slightly less dense than the oceanic one. This is hard-packed rock. This is slightly less hard-packed rock. Now we can get into boundaries. That's okay. They're still both moved by convection currents, which are, I don't think I mentioned it in the other one, but these are convection currents. Because convection is heat, sort of. Convection is the transfer of heat between between like things that are touching. So these are convection currents because it heats up. Well, it's hot down at the bottom. You can't see this. It's hot down at the bottom, and as it rises, it cools down, gets pushed out of the way by the other hot stuff, and then cools as it sinks as it cools, and it's transferring the heat to all the bits around it and the plate. So convection currents. Anyway, yes, destructive, right? Yes, destructive. Okay, the two types of destructive plate boundary are homogeneous and heterogeneous. If there are any of you who are hating towards specific types of people, don't be alarmed. Homo is Greek for same. Hetero is Greek for different. Although it's kind of funny because homo in Latin, which came after Greek, just means man. So, I mean, yeah. Same and different. Also, if you hate gay people, get out. Go watch a different video. I mean it. If I see any of you, I will actually hunt you down with all my gay friends, and we'll beat you up. For the people who are still here, hello. So this is essentially a fancy science word for something that is the same and something that is different. Also, I'm pretty sure these are spelled correctly. Yes, yeah, they are. Yes, they are. They are spelled correctly. I double checked, triple checked, triple checked. So, homogeneous and heterogeneous. Genius. Yeah, homogeneous. Homogeneous and heterogeneous. Heterogeneous. This is the easy one. You have a really dense oceanic with the ocean, and you have a less dense continental with all the people there. They're standing in water. That's okay. Imagine I drew this better. Like that. There you go. Boom. That's all the coastlines in Britain look like. There we go. So you have a less dense continental and a more dense oceanic that are being pushed together. Now, simple physics, less dense goes up, more dense goes down. So what this actually looks like is more like what we had at the start with the continental and the oceanic. So as the continental goes up, the oceanic goes down, and this is all mantle. All of this in here, all the way around here, is all mantle. And as the oceanic plate gets pushed into here, then it all melts in here. So there isn't just like massive stabs of oceanic crust going all the way down into the mantle. What does happen is, as they're going across, well, which one should we talk about first? I know, I'll get a coin. I got a 2 pence, because it's really big. Okay, so heads for volcano? Sure, heads for volcano. We're doing... Is that the heads? No, that's the heads. We're doing tails, so earthquakes. Earthquakes. So what happens... Where'd my pen go? There. So what happens is you've got this plate sliding up and over the oceanic plate, and that's, if you rub your hands together like that, there's lots of friction and it's very hard to move, which is made worse by the fact that this isn't flat. This isn't 2 sheets of like paper sliding over each other. The interface here is so rocky, it's, well, you know what it looks like. if you know what the bottom of the ocean looks like, or a rock. Bunch of rocks, bunch of cliffs. There, well, the bottom is slightly, like, less jagged because it's like been melted away and stuff. So it's not, yeah, it's basically, there's lots of friction that happens between it, and sometimes these get stuck together. So if you've got a crack like that, and if you have your continental plate runs up along here and then gets stuck along there, along each of these bumps, if this one's moving down, that one's moving up, they're essentially like that. So yeah, they're stuck. The plates are stuck together. However, you still have the convection current moving this one this way, and that one that way. So they try to move. They can't. They're physically stuck together. And rock isn't elastic, but there's a lot of pressure going between them. So you have all of this built-up mass of the continental plate squishing. And to squish a rock, let alone a continental plate, that's a lot of force. The oceanic one is denser, so it takes a lot more energy to squish that one. So at this intersection, right there, you have just a little bit of tiny little bit of pressure, and eventually what happens is that cracks off. Now it can move. It wears away all of these bits, and now if you imagine the hands again, if you do that and then imagine doing that and you're still pushing, it goes whoop and jumps. Now, the ground underneath your feet, jumping suddenly like a couple of centimetres off, with all of the force of the Earth's heat moving two things together, and them not being able to, it's enough to shake so many thousands of hundreds of millions of tons of solid rock. It shakes. It like physically shakes so much, and that spreads across the entire plate. Well, not the entire plate. Well, sorry, I need to drink something. Okay, where was I? Yeah, okay. So it shakes a lot here, because this is where the pressure is built up, but as it moves along here, it like dies out, because it's moving all of the particles from the plate. It's moving them a lot. So it sort of like dies out, so it gradually gets less and less the further away you are from the centre of the earthquake. This happens on both plates, which is, like, it's devastating for anything on top of the continental plate, like, I don't know, buildings. Imagine that's like a building. It shakes. It does that. Which for a building is... Okay, so imagine you have this building, which is very tall, precariously balanced on your hand. Okay, do that. It breaks things quite a lot. There are some things you can do, like if you detach your entire building from the floor and you make like a dip, and then you have what's essentially a massive spring. Not really. No, you can't see that. It's glaring. So it's essentially a giant spring attached to the ground, and then you put your building on a plate there. So that's your building, and you put it on a plate. When this moves side to side, my pen's going. When it moves side to side, it moves the bottom of the spring, but the top of the spring stays very solid, very stationary, because the spring, essentially there's a lot of momentum for here, so you need a lot of energy to move this from its starting point because it's very heavy. So as the energy moves up the spring, it gets less and less until it reaches the top, and then it doesn't have enough energy to move the building to a particularly disastrous extent. Another thing you can do is, if you have your building like, there we go, like that, and it goes down, it's a really tall building, and you attach a pendulum to the top of it and put a massive weight at the top of your building, then when the bottom moves, this stays still, and then it pulls. If you imagine it goes now at an angle, like that, the ball pulls the building back across rather than it just swinging out. Well, it does a little bit, but it keeps the top of the building still, which means that as the bottom's moving, the top is less likely to... Because the top is the worst bit. When you move this slightly like that, it sort of sways, so the top point of the building can go from here all the way across to there, with the bottom only moving a tiny little bit. So as this stops the top from moving around, it more does that, which is a lot better for the building. And consequently, all the people living in the building, which stops it from collapsing and killing hundreds of, like 1,000, an amount of people, which would be bad, which is any more than 0. So yeah, that's an earthquake. It happens between the rubbing bits. Yeah, I mean, it's basically conservative as well. You've got your wiggles and your other wiggles, and they follow the same line. That one's going that way, that one's going that way. They get caught on each other, like this. This, as that's going up, wait. Make this a better example. That's going like that. You've got this big chunk here. As it's moving up that way, down that way, it gets caught on this bit. It builds up a bunch of pressure until that breaks off, and that breaks off, and then they jump and release all the pressure and go, and then like stuff happens. People die, stuff gets broken, all that horrible stuff, which means you have to spend millions of trillions of pounds fixing things, and can ruin a country. So that's how earthquakes work. You don't get them at... Oh, hang on, yeah, my diagram was wrong. You don't get earthquake... Well, you can get earthquakes, but they're like worse ones. Worse in that they're worse at being earthquakes, not worse at, like, for people. So you don't get many and big earthquakes at constructive plate boundaries, because they're just moving apart, so there's no, like, there's nothing that can stick if they're just moving apart. Yeah, basically destructive is the best one to show things. So, as I mentioned before, put this down, the oceanic melts. Now it takes a lot of heat to melt a very dense plate, but as we saw earlier, 1,000 degrees is very likely to do it. It's very likely to melt this. However, what I didn't say earlier was that there's water here. All of this is water. It gets sucked down, and it like dribbles through the cracks through here, and then some of the water comes down with the plate. Now, water freezes at roughly 0 degrees. It boils at roughly 100 degrees. In fact, yeah, at 0 and 100, but like, if it's impure, then it's completely pure water. There we go. Freezes at 0, boils at 100. At 1,000 degrees, it's quite a lot. Yeah, there's not very much water coming through here, but then imagine it's kilometres across, and it's so jagged, but a bunch of water gets down there, you have a massive build-up of pressure from both this plate smashing into the mantle, it melting, and then rising. So essentially, what happens is that melts as well, and then you have a bunch of superheated magma from this plate added with a bunch of superheated water vapour, which, as you can see, rises. Now, you've got a less dense, I keep drawing circles, I don't know why, a less dense continental plate here, with a bunch of pressure under it. So, what's exceedingly likely to happen is all that pressure hits here and goes up. Now, as you might see, there's a continental plate in the way. So what happens is it burns through here, it burns a massive hole in the crust. That's at some points 70 kilometers thick. So you can just imagine how much pressure there is here. So it forces its way up through here and spurts out the top and burns down this building, which collapses. I just didn't want the building there. So it spurts out the top. Now what happens is it has all this pressure, it escapes. So it all shoots out the top with all the magma, and it forces its way out the crust, and then all the pressure's gone. So all of this magma comes out here, and it cools down and forms just a layer across the top. Now, if we remove this, we have a path for pressure. So, if all of this pressure is gone, what happens? The plate keeps moving. It keeps going down, and it keeps melting. So, that bit disappears, gets replaced with more pressure, which moves up and bursts out the top as more, well, this is the magma going up. As soon as it exits the crust, it becomes lava. I bet you know what lava is. I mean, I'm hoping you know what magma is as well, unless you weren't paying attention to geography, or you're not at that level of schooling yet. Hello, if you are, and hello if you aren't. So over time of this melting, pressure going up, it builds up these layers, and layers, and layers, until you have a volcano. Can get rid of different. This is a volcano. Magma comes out, lava comes out the top, ash comes out the top, in a cloud, and it's made up of cooled lava and ash that's all fallen down. So you have your earthquakes there, and then as it melts here, it goes up and it forms a volcano by breaking through the crust, and that's what the heterogeneous one is. The homogeneous one is, it's sort of the same. You don't get volcanoes though, because what homogeneous means is you have two of the same plate rather than two different plates. So if you have, it's delightful. If you have two continental plates that are moving together, continental, hang on a second. Okay, an example of constructive against constructive is, funnily enough, the Himalayas. Because what happens here is, essentially you have two, put these down, you have two things which are the same density, so they do that. Now, one will be denser than the other, but only by a little bit, because things get, like the plates get denser as they grow older. So the denser one will sort of do that. So this tries to slide over the top, and it'll end up doing that, so the plates warp like that, and this pushes up minerals up onto the top, and creates a little something called fold mountains, like the Himalayas. That's a terrible fold mountain. Yeah, so that one goes up into the mountains, and that one sort of bends down underneath it. Because they're roughly the same density, it doesn't actually go straight down into the mantle like this one. What it does is basically just slides underneath it like that, rather than doing that. So this doesn't melt, or at least it doesn't melt much. You just get a thicker bit of crust as the plates join together. And mineral is pushed up to the top. And some of this, basically this pushes up the bottom plate as it's going over the top and pushing that one down. So some of this takes the place of this bit as it goes up and forms the Himalayas and other boundaries. These ones are relatively, just big mountain ranges, like the Himalayas. I've said that 3 times. I don't need to keep saying it. But the plates move together. You do get earthquakes because of the friction in there. But as I said, it doesn't melt, so there's no actual volcanic activity because there's very little pressure going up. So you just get earthquakes here. When you have an oceanic and an oceanic, it does much the same thing. So that one goes up, that one goes down, and it's because of the same reason as that one's older, that one's younger, so that one's more dense, so it goes down. And this is why you get ridges under the sea, like the Mid-Atlantic Ridge, I think. Pretty sure. I haven't checked that, but I'm pretty sure that's right. You get the Mid-Atlantic Ridge, where you get another like underwater fold mountain. And yeah, those are the two types of destructive boundary. Questions, anyone? Should really stand over here. There's so much more space. But I mean, doing that and drawing like that. I mean, I could draw like that, but I'm mildly ambidextrous, but not like good. So yeah, questions? Anyone? Anyone in the class? No, good. Yeah, I mean, if you do have any questions, I would suggest Googling them, because this is, I mean, it's not simplified. Well, it is simplified. In fact, it's very simplified. It's very oversimplified. Not that this isn't what happens. Like, I'm not just saying it does this and it does something completely different. But this is, I mean, you could go forever of just reading about tectonics. I could make this like an hour-long video documentary on stuff, but then you might as well go watch like National Geographic or something. But yeah, this is how it works. If I haven't explained anything well, then ask questions about it. But I would just suggest looking things up if you're interested in this sort of thing, and you don't think I've explained something in the depth that you need me to. So yeah, that's destructive. Moving on to constructive. In fact, not moving on, because I've just thought of something. There are 2 types of volcano, that I showed earlier up here. Roll the clip, or like an image. I've written volcanoes, and then a volcano, and a volcano. There are 2 types. That's a composite volcano, because it's made up of many layers of volcanic excrement. I see you laughing. Yeah, it's made up of many, many layers. The other one is called a shield volcano, which we're about to see on constructive boundaries, so I thought I might mention it before we got there. Now, onto constructive. Okay, constructive, here we go. Now, there's only one type of constructive, because it doesn't matter which plates it is, because they're just moving apart, they're not interacting in any way. So, if you imagine this is like the start of a plate, start of 2 plates, where it splits apart. So, this is like the base case where you just have plates at the start. So, you have these 2 plates, they're moving apart because they're convection currents. So you've got your 2 plates moving apart, Drawing in all the arrows. So you've got your two plates moving apart, and this is them through time. At the moment, they're stuck together, so there's no space between them. And then they move apart a little bit, and then you have all this hot magma under here, and it bursts upwards through the gap there, and sort of settles on the ground there. Now, I do need to be on this side. When they move further apart, you have more going up, and you have your layers. That breaks through there. I don't know why I'm doing this. I have a... Okay, and it breaks through the top, and then it builds up and over. So it goes like that. And then the bits on the side solidify and form the new edges of the plate. But the centre can't solidify because there's all the hot magma pushing up out of it. So what you get here is a sort of that shape, where you've got these gentle sloping curves off around the side, and then at the centre of the plates there, it just shoots up and out the side, out like that. This is going to be a very broad generalisation, but most of them are underwater, so you don't see this on land. All of this will be covered underwater, probably. Yeah, this is this is a shield volcano because it's more flat and sort of that shaped with that, as opposed to the more traditionally volcano shaped composite volcano. So that's constructive. There are mild earthquakes, but not anything that needs bothering with. And then conservative, we've already spoken about. So that may be the end. If it is, on to the end. If it's not, if there's something else I can think of to say, then on to that. Okay, I've decided to end it off here because, as you can see down there, it's getting on a bit. I think my estimate for how much footage I've got to be used is like half an hour, but I'm going to speed it up to the usual 1.2 that I usually do, and you can watch it at like 2 times speed. I don't care. I'm absolutely fine if you watch any of these videos at like 2 times speed. I would do that myself. But yeah, I'm going to speed it up so it won't be like half an hour long. Fingers crossed. All my fingers crossed. All my arms crossed. It won't be that long. The next H&TheWs episode is likely to be on rocks. I mean, this was on rocks, but like more specifically rocks. And we might even get into fossils, so stick around for that. Yeah, as I said before, any comments, leave a comment. If you absolutely hate what I'm doing, leave a dislike there. Yeah, essentially, give me feedback if you have any. I'd love to know how I can make this better for people, because I think it's good. I'm not everyone, so if you absolutely hate this and want me to never do this again, yeah, essentially. That concludes it for Tectonic 2 Electric Boogaloo. And if you don't get that joke, we can't be friends.